welcome our next speaker, Professor Myungshik Kim from Imperial College, who will tell us about quantum control of phononic states and very small things shaking.
Okay, thank you very much. I think it is, I'm very fortunate to give a talk just after Ian's because there are, I think I found lots of overlaps. So in terms of content, I don't think there is much overlap, but in terms of terminology, there is a lot of overlap. And at the end of Ian's talk, he talked about this controlling phonons and using that Diamond's phononic mode for memories and so on. Here, I'm talking about quantum control of phononic states. I'm not talking about diamonds for this, because diamond is too expensive for theoreticians. Let's say even for theoreticians. Here I'll talk about nanomechanical oscillators. They developed these micromechanical oscillators and macromechanical systems, and it is well into industrial scale, and they use it in various applications. That's good. And they push the technology towards the micro regime. So, as far as it is sub-micro, they are entitled to use nano. So they use the word nano, and that's one of the important reasons for this development. It includes like extreme sensitivity. So once you have this nano machine, then they think that the sensitivity must be much better. And they expect high Q values because the mode volume becomes very, very small. Okay, so that's the reason. And now, quantum people think, oh, by the way, if it goes down to nanoscale, why don't we bring the state of this nanosystem into ground state? Okay, so once we reach this, the ground state, well, there can be a lot of things we can do. So that's what they thought, and that's what they're doing. So here is the flow of my talk. First of all, I'll talk about then how to reach to the ground state. Ian already hinted how to do it, but anyways, I'll not repeat it. I'll do it in a different way. And then the next is tomography, and because we have to read out what kind of state we have for this system. And then the next two bullet points are to do with how to control the quantum states of those phononic systems. Okay. Right. Before I forget, I have to mention my collaborators. Okay, from whom I have been learning a lot. The two professors at Vienna, including one there, Czesław Bruckner and Markus Aspermeier, and two students in Vienna, Igor Bikowski and Michael Werner, and a colleague of mine in Korea, Myungshik. Okay, first, let's start with cooling. How to bring this nanosystem into a ground state. Well, first of all, I found that there are some unfamiliar faces. I heard that there are like computer scientists here. I'm sure that even computer scientists know about ground state, but just in case, by ground state I mean that for the phononic mode there is no thermal excitation at all. So it's sitting in the lowest energy level state. So that by means of like detecting energy, we don't see any energy, even though we see the fluctuation. Okay, so that's what we want to achieve. So the basic scheme to cool down is to use fridge. That's true, but in quantum mechanics, normally we think that that is not enough. So what do? We we use this scheme, which was developed by Einstein in 1917 first. Even though he didn't call it like that, and his intention was not like that anyway, but in effect, he developed this scheme. Let's think about free particle. I want to bring this free. I want to freeze the motion of this free particle. Here is laser field, and here is the particle. They travel in opposite direction, and they meet each other, and then they interact each other. By interaction, I mean that this particle absorbs the photon. And then, well, once it absorbs energy, it has to emit, right? And in which way is a question, but it has to emit the photon. And before we go into the emission, we have to think about the fact that they travel in the opposite direction. That means there is Doppler shift, which means that this atom will see the laser field as if it has got a little bit higher frequency. Okay? As we see in the Doppler effect of the sound. And after it absorbs the photon, and it realizes that, oh, it is not the frequency I thought of. But when it emits the photon, then it has to follow the way that it can transit down to the ground state, or the next level down. Okay? So it absorbs a photon which has a lower frequency than the frequency of the photon it has to emit. So the difference comes from its own motional state. Okay? That means it loses once it emits, absorbs and emits a photon. One event it loses photon. Another event it loses motional energy, and next event it loses more energy, more energy, more energy. It cools down, it freezes down. So the emotional. That's the basic mechanism which Einstein thought of in another context. Okay, so that's. But let's assume another case. If not the free particle, but particle in a harmonic potential. Okay, it oscillates in the harmonic potential. In that case, what happens is this. So this is my two-level atom in this potential. So this is the internal energy levels. It's the laser field going in, and it absorbs the photon from the laser field. And that's the photon has got a little bit lower energy than the transition frequency. Okay? But it goes up. Once it goes up, it has to emit the photon based on the transition frequency. And so there is an energy difference between the absorption and emission. Where does the energy from this motional energy, so external energy of the atom oscillating in this harmonic potential. Okay, so that's called sideband cooling. The earlier scheme for free particle called Doppler cooling, and this sideband cooling. So we can see that there are two important ingredients for cooling. One is redshift. There must be some energy difference between the transition frequency, or the frequency, the natural frequency of the internal energy levels of the atom or the particle, and the field which excites the atom. So there should be some energy difference between the two. And it has to be, the energy of this external field has to be smaller than the transition frequency of the internal energy levels of the particle. That's called redshift. And the next one is spontaneous emission. It has to emit the photon in a spontaneous way. Okay? So there are two important ingredients. And that can be described by this mathematical notion, that is sigma plus, which means that the state going up from lower state to the upper state. That is right. While it absorbs the, it lowers the motional energy level of the system, of the particle. Okay? So that is lowering operator for this phononic modes. So that's important process. Let's go into this nanomechanical oscillator. This is my nanomechanical oscillator. This one moves. And here I have another mirror to form an optical cavity between the two. Okay? This is fixed and that moves. And what I want to do is to bring this nanomechanical oscillator state down to the ground state. Okay? So it's not the atomic motion in harmonic potential, but there's nanomechanical oscillator motion in harmonic potential as well, because it moves like a harmonic oscillator. So the earlier slide, here, that goes into nanomechanical oscillator. And where is this? In this system, here, the motion here is coupled to optical field inside the cavity. Okay? And the external driving we had is here, the field, the input laser field. So input laser field, denoted by this green color arrow, goes in, and here is and then here is the system, and that is the nanomechanical oscillator we want to see in a ground state. Okay? So if we give less energy to this cavity, then it normally accommodates. Now our redshift is done, right? And the next thing is we have to see spontaneous emission. Here we don't see spontaneous emission, but once the photon leaks out from this cavity, that's like spontaneous emission. What is spontaneous emission? Well, one thing is that you don't know which direction it goes out, but more importantly, it goes out and never comes back. And the photon goes out and never comes back. That is fine. It's like spontaneous emission. Okay? So it goes in, and this energy is smaller than that energy, and goes out like spontaneous emission. And now we have satisfied two requirements for cooling. That's it. Okay? So this energy has to be smaller than that. The energy which can be accommodated by the optical cavity. Okay? In mathematics, the interaction Hamiltonian for that, including the nanomechanical oscillator motion, comes in this form. Okay? That's the photon state, and delta here, delta is the energy difference between the external field and optical cavity field, and omega m denotes the frequency of the mirror, and all here there has to be h bar here, but I've taken h bar equals 1 in this Hamiltonian. And that is the mechanical motion Okay, another harmonic oscillator. And that's my interaction between light field inside the cavity and mirror motion. And the last term is important because it gives the coupling between the optical field inside the cavity and the nanomechanical oscillator. That's XX position-position interaction goes into that form, and then it's expanded in this form. And now we take the rotating frame. So by taking a rotating frame, A transforms into this A exponential minus I delta t, and then B goes into that form. Then once we transform in this form, in this, then the Hamiltonian here becomes like that. Now we can clearly see that when delta is the same as omega m, the exponential t here becomes 1, and while when delta is the same as omega m, it becomes 2 omega m, and exponential function, as you know, oscillates very fast, so that we can ignore the second term while we keep the first term with time-dependent term drops out. Okay? So that is the thing. So this clearly, A is the operator for the photonic field, and B is the operator for the mechanical oscillator motion. So lowering the mechanical oscillator motion from upper state to the lower state, and then photon comes out. And if the photon stays inside the cavity, bad luck, but it comes out, then we've lost one phonon. Okay. So using that kind of scheme, the groups around the world tried to lower down the phononic modes, and that's we are looking for the region of 0 phonon number, and they started with like 10 to the 10 mean phonon number to here, and then all these things. Okay, that's a logarithmic scale, so it's not as bad as. Okay, so that was till 2009. But if you recall what Ian said in his talk, said that diamond, terahertz, and there is no mean phonon. Okay, so if we increase the terahertz, is because this here, this x-axis here is the frequency, and terahertz must be somewhere here, right? And at the same temperature, as the frequency goes up, the mean photon number drops down exponentially. So what they did in 2010 is, oh, let's forget about this. How about just increase the frequency? So you increase frequency from tens of million hertz to gigahertz. Okay, so the n bar is already 0.07. Okay, so that's what they did. That's great. And at the end of their nature, and surprisingly, this paper I found that has been cited already 200 times. Quite amazing. And at the end of their paper, they say that the results we report here provide strong evidence that we have achieved reasonable quantum control over a macroscopic mechanical system. We note that full Wigner tomography of the resonator states would provide further strong evidence. Right? Then here, but how do we then bring? How do we do this? How do we read out this the state? Okay, so that's important because the evidence they had was like Rabi oscillations. Okay, and it is a good evidence, but the better a full picture of the quantum state is will give them much stronger evidence of their having reached the ground state. Okay. So I'm anxious about the time. When did I start?
So a little bit late. So you still have 16, 17 minutes.
17 minutes. Okay. All right. Okay. Right. So to read for the tomography, we need something like a Wigner function. In the earlier talk, you probably saw that the one of the first slides to increase the entanglement, a photon was subtracted here and there, and at the end you saw like some pictures, which has the axis, x-axis and the y-axis as well. That's the two-dimensional. That is the picture of Wigner function. Wigner function gives the full the information on statistical properties of a quantum state. To measure that, what is important is to be able to measure the quadrature variables. Okay? So quadrature is defined in this form, and that's when theta is 0, it is x operator, and when theta is pi over 2, it is p operator. And when theta is between 0 and 2 pi, it is between those two axes. So in phase space, we have this x and p, that's phase space we know of, and we have to be able to measure the probability of p of x and probability p of p. And also for all other axes, then we'll be able to reconstruct the joint probability function, and that's what we want to do. And to do it, we have to be able to measure this x. And how do we do that? For optical field, in earlier talk, they used homodyne measurement. For this, we don't have homodyne measurement. So first, we have to take this interaction Hamiltonian between the light field and mechanical oscillator. You know, this is the interaction Hamiltonian we had in the earlier slide. Okay, so once we have that, x of t. So what we can measure, we cannot measure this one directly. Okay, what we can do is that we have to see the field having interacted with the nanomechanical oscillator, and by measuring the light field coming out from the cavity, we can infer that this was probably the state of the nanomechanical oscillator, or this was what was happening there. That's what we do. Instead of just directly measuring, we have a ruler there and then measure it, and then we have a scale there to measure it. That's what you do. Okay. So this is what we measure for the light field coming out from the cavity. And in fact, can we really have full information on the nanomechanical oscillator by measuring the light field? Well, if we see the evolution of the light field, or x operator of the light field, we'll see that just it's the same as the field going in. So does not have any information on mechanical state. But if we take the p operator of light field, then it carries information on that. If chi is large, chi is to do with the coupling. And if coupling is large, okay, then this second term dominates this, so that the p quadrature of light can directly give the information on the x quadrature of the mechanical state. Okay? So that's can do and measure that. Another good thing about this system, well, bad thing is that we cannot directly measure the mechanical state. We can always infer the mechanical state, but not really to measure it. But that can also give some good aspect. That is, because we don't really measure it and destroy it, we can reuse it. Okay? We have some connection, and then we have measured something else. That is still there. Of course, it has been collapsed into something. If we can measure and then collapse into something which is useful, that's great. Okay? So we use the same Hamiltonian, that's fine. And what we found is that after one measurement, the mechanical state collapses into a squeezed state because of the interaction Hamiltonian. Okay? So that's a good thing. So this we start with, and then we squeeze it, and then we wait till it rotates to this point and squeeze it to measure it again. Then we don't have to think about the sideband cooling and all those things. We can go into a nearly ground state level by two measurements. So that's a good thing. Now, go to the next part. That's this is one of the slides I have already shown you, cooling. And here, what I did is that at the end, so we use this part, the first part, to cool it down. How about the second part? Okay, the second part, if my delta, so the detuning between the external field and cavity field, is not the same as omega m, but the same as minus omega m. Let's say omega m is minus detuning. That's possible, right? So then this will be fast oscillating, and that will be slow oscillating, right? And what is this term? That's A dagger, B dagger. That means that when this is the when photon is created, B dagger appears. That means that phonon moves up. Phonon state moves up from a lower state to an upper state, right? So in the cooling, what you want to do is we want to take out energy as much as possible. That means phonon state going down from upper state to lower state, and further lower state and lower state. That's what we want to achieve in cooling. But let's say that we want to warm it up. We up. So second part is warming, and that's cooling. Or I can, Ian used the word subtracting a photon, right? So this one is like subtracting a phonon, and that is like adding a phonon. Okay. So how about this? We do the thing, but we don't know if we have subtracted or added. We don't know. Okay? How do we do it? So this is a field which is detuning is the same as plus omega m, and that is the field. Detuning is the same as minus omega m. So that will give you addition, and that will give you subtraction. And those two light fields going into the cavity, and having after the interaction, we measure the photons, the photonic field out from the cavity. Okay, that's what we do. So had this one been interacting with the nanomechanical oscillator, it should have been a B operation, subtraction operation, and had it been this, it should have been the addition operation. So, but by detecting the photons here, we don't know which operation has happened. So the operation itself going into the superposition of A operation, or it should have been B, right? Because I used the B operator for the mechanical oscillator, but let's say, okay, that's B and B there. Okay. And then we do a little bit of more, can also add unit operator, which means that nothing has happened. Okay. So that's the thing. Let's stick to this A operation and A dagger operation. I'll call this is input field, and that, that's the initial preparation of the nanomechanical oscillator, and after the operation, that is the final state of the nanomechanical oscillator. Let's see what kind of relation these two states have, and check the overlap. We check the overlap, and that's going to be like that, and then that's if this is the same as that, okay, then we know that this is same as that, that's 0, and the input state, so the initial preparation of the nanomechanical oscillator is orthogonal to the final state of the nanomechanical oscillator. Okay? For that, what do we need? We need the information on just this theta in this here. Okay? So, whatever state you give to me, I'll give you an orthogonal state. Here, Ian also mentioned continuous variables. Most, I think, probably this morning's two talks are the only talks. Probably not. There will be Marcus +/- talk. But anyways, one of very few talks on continuous variables. Anyways, we use this continuous variable state, which is defined in normally in infinite-dimensional Hilbert space and continuous spectrum. We use whatever continuous variable state you give to me. I'll give you back the orthogonal state, and I can also give you back any superposition of the initial state you give to me, and then its orthogonal state. So if you want to use a continuous variable as a qubit state, that you can also do. Okay, right. So the last part of my talk is will be continued one from another by two other talks in this workshop. So I will just briefly mention this, and you will see the rest in my collaborators' talks. So what we want to do is nanomechanical oscillator. If we bring this down to the quantum mechanical level, why don't we test the commutation relation between X and P? Because it has got X and P, and commutation relation is one of the most important mathematical structure of quantum mechanics, right? So, and uncertainty principle and so on. Okay. Here, about the same setup, but the difference is that we can do many interactions. So the interaction Hamiltonian goes in this form. Well, if you are observing well, then you realize that something has happened to this operator. It was X position interaction, but now I have intensity the position interaction. In fact, intensity position interaction is the right form, but some approximation has gone into X form. So that's the let's take this more, say, rigorous form, and then take this Hamiltonian, And in between, so interact with the nanomechanical oscillator, and pulse comes out and travels around this circuit, and then goes back and come out, and then goes back and come out, and it does 4 times. In between, while the nanomechanical oscillator is waiting for the next interaction, it freely evolves. Okay, so that's the situation. It interacts, and it moves out, and freely evolves. Next one comes in, interacts, and freely evolves, interacts 4 times. So the first interaction, second interaction, third, fourth, because of the free evolution, had the first interaction been X in the mechanical oscillator motion, next one goes in the form of P. That's because if it interacts here, the center, or equilibrium position, it goes out at this turning point. That is like the initial state X, for instance. It goes back and then goes out. So in effect, in the rest frame, that's going to be like this. So that's now, if you get rid of these operator notations, then you will see that this minus will cancel out this plus, and minus will cancel out this plus. So all these things will sum up as unit operation, right? But we know that X and P do not commute if quantum mechanics is right and commutation relation is right. And we know that that's the just 2 operations here will give this operation, and then that. At the end, you will see that the whole thing together sum up with only the commutation relation. The commutation relation of the 2 operators will change, will give the change of the phase of the outcoming light field. So by measuring the phase change of the outcoming light field, you will measure the amount of the value of commutator. That's the whole scenario. And because it is a massive particle, we can do quite a lot, and that part will be continued in other talks, I hope. Okay, so in my talk, that's I wanted to show you how to cool it down, and how to read out, and how to control, and how to manipulate the phononic state of the nanomechanical oscillators. Thank you very much for your attention.
Thank you, Professor Kim, for this very instructive talk. Are there any questions?
Can I ask 2 questions or not?
One at a time.
Okay. The first question is, you showed that measuring quadrature amplitudes could reduce the phase space uncertainty. So, is that a real cooling mechanism too? And did you start from a mixed state and you end up in a pure state?
Yeah.
In just 2 steps?
Then that is right. So if I can go back. Okay. So the other question is about this is the sequence of measurement. So this is the preparation of the initial nanomechanical oscillator state, which is thermal, with the thermal mean for thermal number 10. It's nowhere near to the ground state because n bar has to be 0. And one measurement will squeeze it. Then the question is, okay, now you can squeeze it, but do you really reduce the thermal photon number? The effective thermal photon number goes down to 1.5 by 1 measurement. So it really goes down. That's yeah.
And is that conditioned on a particularly precise measurement of a particular value of the quadrature amplitude. So there's effective filtering as well, because
That's right.
okay.
We have to measure P. If we measure X, no, but we measure P. And also the first one is rather easy because you can choose. But second one, if you have to find the right time where so this will freely evolve and it comes here and then you have to measure the second one. Otherwise, you will not have a good result. So that's the thing. That's because the whole thing, the operation, if I take only the operation for the nanomechanical oscillator, it's not unitary.
Was that both questions? Or?
No, that was only one, but if there's no other question, I'll ask another.
No one's faster than you.
In your last slide, you illustrated this way to measure the commutation relation. And there's an interesting feature in that, of course, to do with the space phase trajectory that is non-linear in the photon number in this cavity. So my question is GT bigger than 1 or very much less than 1? Is there a coupling constant?
The GT here, is it, it is in the experiment, it is bigger than 1. It can be like 2. Yeah, that is what we hope, and yeah. Right.
Yes, think about other systems like cool. How does the Q factor of the optical cavity and the rest of the vibration and such like? What determines the strength of G? What parameters do you try to optimize to get a large amount of G?
So your question is, what is the typical parameter value for Q?
How do you optimize the optical properties of this cavity to maximize the cavity strength?
Oh. I think you have to use mirrors. That's, I think, coating would be important, and also the distance would be important as well. So because if that's yeah.
So what I mean is, as I increase the quantum factor of the cavity, does the G parameter increase as well?
Yes. Yeah. Because it depends on how long this pulse stays in the cavity. That's right. So yeah, and how compact it is. Yeah. That is right. But for different experiments, I've shown you a few possible experiments, and so experimental proposals. And depending on the proposals, you don't really need to have large G. And sometimes you don't need to have, you need to have large G. For instance, to see the squeezing, you need large GT value. But if you do not want to see that, for instance, subtraction and addition, that kind of thing, you don't need large value of that. Because when it is large, then it's not subtraction and addition anymore. Yeah.
But G is basically the round frequency.
It's I would say coupling. It's not two-level system. It's two harmonic oscillators. So I would be not very comfortable to call it as simple Rabi frequency, but it's coupling, sure, yeah. And coupling becomes Rabi frequency for some step.
Approximately.
Oh yeah, yeah.
Good. If there aren't any questions, then I'd like to delay any further discussion to coffee. Let's thank both speakers in the session again.